Assalamu alaikum warahmatullahi wabarakatuh. Thank you for letting me have the chance to present my research project under the title Multilayered Electrode Preparation using Thermal Evaporation Technique to Fabricate Supercapattery with Ultra-High Energy Density. I would like to quickly introduce myself. My name is Muhammad Kauban. I am undergraduate student at King Fahd University. I worked under supervision of distinguished Professor Muhammad Ashraf Kundal at Physics Department. He was awarded a Saudi citizenship by a royal decree by the Majesty the King Salman for his scientific achievements. A worldwide effort to address the issue of sustainable energy supply is now focusing on electrochemical energy storage, or what's known as EES, and material development. To address the current scenario of renewable energy intermittent, modern EES technology research and development is required to achieve the goal of fabricating an advanced and efficient energy storage device for sustainable supply of electricity. This schematic diagram represents our supercapacity. A symmetrical device with the same material on both sides was made by thickness-controlled thermal evaporation method, using a manganese oxide modified activated carbon electrodes, which were further improved by the addition layer of vanadium oxide. This schematic diagram represents our thermal evaporator setup. The powdered manganese oxide and vanadium oxide were compressed to a circular pellets. These target pellets and aluminum substrate were placed inside the thermal evaporation chamber under a vacuum of 10 to minus 4 torr. The fabricated electrodes were characterized using SEM and EDS to study their morphology, structure, and chemical properties. The device also have been characterized by performing a cycle voltammetry, electrochemical impedance spectroscopy, galvanostatic charge-discharge analysis. In this image, we can clearly see activated carbon electrode coated with thin layer of manganese oxide and vanadium oxide. The image shows micro-sized particle of activated carbon coated with the metal oxide. The elemental composition of each element used in the fabrication of the multi-layered electrode is analyzed using EDS spectrum. Clearly, the figure shows all elements used to fabricate a supercapacity. In this figure, we show the cycle voltammetry results of multiple supercapacity analyzed in 1 volt potential window. In this figure, we see the specific capacitance as a function of electrode material in the form of a bar chart. Clearly, we obtain the highest capacitance of 145.6 farad per gram in the multi-layered electrode of manganese, vanadium manganese. Examining the charge-discharge profile of the device in 1 and 2 volt potential window, the device displays a constant behavior even in high potential window while displaying a substantial specific capacitance of 129.5 farad per gram. Here in figure A, the EIS data was used to draw the plot of the fabricated supercapacity, and in figure B shows the phase versus frequency graph, also known as Bode plot, used in investigating the capacitive or resistive nature of the device. The phase angle close to 90 degrees at lowest frequency, indicating the capacitive behavior of the device. And in figure C, the theoretical curve fits very well with the experimental data. It is really also worth mentioning that the hydrophobic nature of carbon electrodes were altered by the metal oxides coatings. The selective coating approach not only introduced radix effects, but it also transformed the carbon hydrophobic nature to a superhydrophilic nature as shown in the figure. A graph is made between the device energy density and power density, known as Reagan plot. The ultra-high energy density verifies the use of our device as a battery, where a huge power density confirms the supercapacitive use of our device. In conclusion, Three main points have to be mentioned. Firstly, a supercapactery with a high energy density has been successfully constructed using activated carbon, manganese oxide, and vanadium oxide. Secondly, using a potential window of 1 volt, the constructed device exhibits a high specific capacitance of 145.6 farad per gram, which raised to 183.5 farad per gram at 2 volt applied potential. The constructed supercapactery shows an ultra-high energy density of 101.9 watt-hour per kilogram, which is much higher than the energy density of a carbon-based supercapacitor of the same size. Thirdly, a hybrid electrical system might be benefited greatly from a device with a unique layered structure that provides a high energy density and power density in the same time. Definitely what motivates me and my team to work on this project is the future. In order to keep up with our rapid advancement of electronic systems, effective and dependable long-term energy storage technologies are required. Batteries and supercapacitors alone cannot meet the energy demand of a modern technology. So, supercapacitors is a very important technology to be developed to match these goals. In the end, I would like to thank my university, my supervisor, and Abu Dhabi University for letting me have the opportunity and chance to present my work with you. It was my great pleasure, and hopefully we will meet you once again.